Hello dear friends, welcome my channels. Today's discussions is topology, homeomorphism. At first you have to learn homomorphism. We would like to go forward to back to our particular roots. We understand that indeed roots are something which we always try to go forward. This is the Greek term of homomorphisms. This is the homeo plus morphi. Homeo means together, means jointly, and morphi means form, shape and figure. It is actually an assimilation of two terms, homeo, together or jointly. Learning the roots are equally important, so these Greek terminologies actually gives an idea to you that what is homomorphism. Something which carries a form on a figure. So here on the right hand side of the screen you can see that a blended figure which hold hands together. So can understand this is a symbolical meaning of homomorphism. Now when we talk of the term homeomorphism, we actually is going back to the roots, that is Greek one, omia. Omia means Tito, and morphi. So omeo plus morphi is equal to homeomorphism. With the same morphi, it means together a form or shape on figure. Now we come to isomorphism. It is also taken from this Greek term, and it means equal plus morphi. Which would be common for both all these. Isomorphism means equal shape. Homomorphism means together shape, and homeomorphism is similar. Congruency is replaced by topological invariance. This is the very important. Congruency is replaced by topological invariance. Example, this is the example. This is the example. This shape is the homeomorphism example. A property preserved under homeomorphism. Now, isomorphism. In mathematics, an isomorphism as a structure preserving mapping between two structures of the same type that can be reversed by an inverse mapping. Isomorphism is a bijective morphism. Now this is the point. A group x1, x3, x2, x3, x4, we have this, and each one of them are being mapped, or they in corresponding with each other. This is the mapped. Corresponding with each other. This term bijective morphism, what it is actually mean, these things will clear every member of the domain which is on the left hand side is mapped with every single member of the codomain. This is domain, and this is codomain. Graphical isomorphism. Friends, you will learn this graphical isomorphism detailedly in graph theory. I will create a video series on graph theory. Then you can learn graphical isomorphism. these two graphs are isomorphic to each other. Only the second graph is rotated in this direction, rotations in this direction right, so that is why we can call them as isomorphism. Visual depictions of the concept of isomorphism. If you take this graph again, so 2 is a point which is left alone. On the second graph, it is also isomorphic to each other. Now if you take this kind of figure, right, this one, and we take this one and we take this one, so these two figures are also isomorphic to each other. We denote here isomorphism by this. Now condition is the degree sequence, cycle of length, and sufficiency conditions. Now friends, we will discuss isomorphism strict definition. An isomorphism or isomorphic mapping from A to A prime with the properties phi f I alpha 1 alpha 2 alpha ni equal to f phi alpha 1 alpha ni, means if gx in single variable, it will become f gfx, and pj alpha I comma alpha mj is equal to pj phi alpha 1 phi alpha j for all alpha 1 alpha 2 in a all I comma j belongs to j. Homeomorphism. Mathematical definition. A map f such that x tends to y is called homeomorphism between two topological space x tau x and y tau y, if and only if f is bijective, f is continuous, and f inverse y tends to x is continuous. Homeomorphic space. Two topological space x comma tau x and y comma tau y is called homeomorphic if and only if there exists a homeomorphic f such that x tends to y. Theorem. A 1-1 continuous map of a compact space onto Hausdorff space is a homeomorphism. So friends, Hausdorff space. What is Hausdorff space, friends? Now at first you know this is the theorem. Theorem is a 1-1 continuous map of a compact space onto Hausdorff space in a homeomorphism. So what is Hausdorff space? Recapitulation. For every x comma y in x with x does not equals to y, if there exist open neighborhoods u of x and v of y where u and v are disjoint, then x comma tau is said to be Hausdorff space. Compact space. Compact space, a topological space, is compact if every open covering has a finite subcovering. An open covering of a space X is collection of ui, and open sets uj union of j belongs to I, ui equals to X, and this has a finite subcovering, and finite number of the ui's can be chosen which still cover X. So friends, now I want to prove the theorem. Let x comma tau be a compact topological space, and y comma tau, y comma u is a Hausdorff space. U is a Hausdorff space. Let there exist a one-one continuous map f such that x tends to y onto. To prove that f is a homeomorphism, it is enough to show f is 1 1 onto number 2, f is continuous, and number 3, f inverse is continuous. If inverse is continuous, the results 1 and 2 immediately follow our initial assumptions remains to 3. If inverse is continuous. This is our assumption. So if inverse is continuous, so how can we prove? For this we must show that capital F is closed in Y for any closed set F subset X. Let F subset X be an arbitrary closed set. Being a closed subset of a compact set X, so F is compact. So if F is compact, being a continuous image of a compact set. Furthermore, FF is a compact subset of a Hausdorff space Y, U, and hence FF is closed in Y. Thus, we have shown that any capital F subset X is closed. That implies FF subset of Y is closed. That implies F inverse is continuous. Thanks for watching.